17 tasks in this stage. 16 of them read 17 megabytes each and finished together. One read 88 megabytes and is still running. Measured on this machine, 3.5 times longer than the median task. The stage is not finished until that one task is, and nothing downstream starts without it. This is data skew, and in a few minutes you will know how to see it in your own job. So open the stage and look at one column. Shuffle read size and records, not duration. The slowest task read 4,800,000 rows. The median task read 286,000, 17 times fewer. Same code, same cluster, same stage, and one of your tasks was handed 17 times the work of its neighbors. Subscribe if you want more under-the-hood data explanations like this one. Because the interesting question is not which task is slow. It is who decided to give that task all of those rows. Here is the table those rows came from. Nobody wrote a bug here, and nothing is broken. Your data simply has a shape. 8 million rows, over 1 million users, and the median user has 3 rows behind them. One of those values is not like the others. It is the Sentinel your own logging rights for signed-out traffic, and 60% of the rows in the table carry that single value. Uniform is what your code quietly assumes. Your production data almost never agrees, and the biggest key in it is the one that sets your stage duration. Not every join shuffles. This one does. Spark picked a sort merge join, and that plan repartitions both sides by the join key. Every row is hashed on that key, and the hash decides which partition it travels to. Rows with the same key always land in the same partition, or the join could not produce an answer. But notice what the hash never counts. It never counts how many rows a key brings with it. Your Sentinel is one key, so it gets one partition, and it takes all of its rows there. You asked for 200 shuffle partitions, the default. What actually ran was 17 tasks, because Spark merged the small ones first. 16 of those tasks got about 17 megabytes each. One got 88 megabytes. A partition is not an abstraction here. It is the unit of work handed to exactly one task. So when data volume dominates the cost, the oversized partition is the one to suspect, and in this run it became the longest task. All 17 launched within 3 milliseconds of each other, 16 finished together, and the last one ran 3.5 times as long. This is the part that costs you money. A stage is finished when its last task is finished, not when most of them are. So for the whole time that one task is still going, the 16 tasks that finished have nothing left to do in this stage, and the operation that consumes this output has not started. And be precise about what that means. Once the work is concentrated in one unsplit partition, extra executor slots cannot parallelize that single task. More capacity gives Spark somewhere to put other work. It cannot divide this one. Here is the diagnosis, in the order that actually works. Open the Stages tab, click into the stage, and read the summary metrics table. It gives you the minimum, the median, and the maximum of every task metric. Read shuffle read size and records before you read duration. Duration only tells you a task was slow. Shuffle read tells you it was slow because it was given more, which is a completely different problem with a completely different fix. Spark's own skew rule uses 5 times the median as its factor, so that is a fair place to start reading your own table. Before you call it skew, rule out the neighbors. They look identical from here. A task can be slow because its executor is sharing a machine, because it spilled to disk, because garbage collection stalled it, because the rows are the same size, but the work per row is not. Every one of those gives you one slow task in a stage that is otherwise finished. So compare the input. If the slow task also read far more rows than the median, that is strong evidence of data volume skew. If its input looks ordinary, look at spill, garbage collection, and fetch weight. Now the part that catches people out. I ran a groupBy on the same skewed key, over the same 8 million rows, counting requests and averaging latency. There was no straggler at all. The slowest task took the same time as the median one, and the whole stage moved 37 megabytes of shuffle instead of 341 megabytes. Spark aggregated partially before the shuffle. For the hot key, millions of input rows became one partial state per input partition, and only those partial states traveled. Your key was exactly as skewed. The operation was not. Which brings us to the thing everyone expects to save them. Adaptive query execution is on by default, and skew-join handling is on by default with it. In this run, it was already working. It is the reason your 200 partitions became 17 tasks. That is the coalescing rule, tidying the small partitions away. But rebalancing the small ones does nothing about the big one, and splitting the big one is a separate rule with its own conditions. In this stage, that rule looked at your partition of 88 megabytes and decided to leave it exactly where it was. Here is why, and it matters before you rely on it. For its skewed sort merge join optimization, Spark treats a partition as skewed only when two things are true at once. It has to be bigger than 5 times the median partition and bigger than 256 megabytes. Those are defaults for that optimization, not a definition of skew in general. Ours passed the first test and failed the second, so nothing happened. Lower that floor, rerun the identical query, and the plan comes back with skew handling switched on and 55 tasks instead of 17. Same data, same code, one threshold. So what do you actually do? Start one step earlier than the tuning guides and ask whether that shuffle needs to exist. If the other side of your join fits in memory, Spark can send a copy of it everywhere and join in place. I forced that with a broadcast hint. The query went from about 10 seconds to under 3 seconds, with no stage reading shuffle at all. For this join, removing the shuffle removes the hotkey partition that made the straggler. It does not make your pipeline skew-proof, and it only works while that dimension fits in memory. The technique everyone reaches for is salting. Split the hotkey into buckets by hand so no single key owns a partition. It works, and I measured what it costs. The straggler disappeared, the tasks came out even, and the query got slower. To split one side, you have to replicate the other, so 341 megabytes of shuffle became 1.6 gigabytes. That is the real lesson here. Every one of these moves buys you balance by paying with something else, and you cannot know whether the trade is worth it until you measure your own stage. So here is the whole thing in one line. A key that holds most of your rows becomes one oversized shuffle partition. That partition becomes one task, and your stage is not finished until that one task is. When you see it, read shuffle read size before duration, and compare the maximum against the median. Then work outwards. Can this shuffle be avoided? Can the aggregation be folded first? Does the runtime rule actually apply at your sizes? And only then reach for the manual fixes. Parallelism only helps you when the work is divided into pieces worth dividing.